So here's the third part of our review assignment. So they describe this rectangle for us, and they want to know for what value of x is the area of the shaded region a minimum. And this shaded region, when we have a question like this, we're always thinking, okay, what am I optimizing? Well, I'm optimizing the area of this shaded region, but I don't have a formula for the area of that. However, I know that if the shaded region has its area at a minimum, then the rectangle's area must be at a maximum. So that's what I'm going to think about. Where is the area of this rectangle a maximum? And so then that's a little easier to deal with, right? Because I can just say, all right, well, area is equal to base times height for my rectangle. And then I can turn this base times height equation into something more specific for this situation. We know with optimization we can always only have one input, one output. We have here two inputs right away, base and height. But I can write everything in terms of x because the base is 2x going all the way from here to here. That's x, right? Here's one x. Here's another x. That has to be symmetric because of the cosine graph's symmetry. And then the height, I'm initially going to call y. Now that doesn't seem super helpful because you were saying, okay, well, we said we could only have one input variable. I have two. You just replaced b and h with x and y. That's still two input variables. But in the problem, it gives me that y is equal to cosine of x. So my area formula is really then 2x cosine x. Now to find where that's the area of that rectangle is a maximum, I need to take the derivative, set it equal to 0, and find those critical numbers. We'll get to this graph down here in a minute. That's coming in a minute. So a prime is going to equal, I'm going to need some product rule here, so I'm going to leave the 2x by itself for a second, and then make this negative sine of x, plus take the derivative of the 2x, that's just 2, and then leave the cosine of x. And I need to know the critical numbers. Where is this thing 0? This is a difficult equation to solve by hand, if not impossible. So I'm going to solve that on my calculator, and that's what this graph is down here. And I can see it has a whole bunch of x-intercepts, and I should be able to find those on my calculator. But I know that I'm only looking for the x-intercepts between 0, because I'm just thinking about the left-hand side as the mirror of the right-hand side here. So between 0 and this value. Well, because the given graph is cosine, I know that this value is pi over 2. So I'm going to stop looking at pi over 2, which is somewhere between 1.5 and pi here, so between 1.5 and 2 and 3-ish. So there's really only one candidate here, and so I'm just going to use my calculator to figure out what that is. I've already done that. You should be able to. If you need help, let me know. X is about 0.86033,589. Now, I also know that that's going to be a maximum because this is the graph of the derivative, and the derivative is changing from being above the x-axis, a positive value, to below the x-axis, a negative value. So the function itself, the area function, is changing from increasing to decreasing there. So we have a maximum. And if the area of the rectangle is a maximum, then the area of the shaded region is a minimum. And the closest answer we have here is this one. All right. Kind of a long one to get us started there, but that's all right. Maybe this next one will be better. Maybe not. All right, so we have all right circular cylinders. What is the radius of the one with maximum volume? So again, an optimization problem. And what am I maximizing? What am I optimizing? The volume of a cylinder. Often people are thrown off by the right circular cylinder. That just means what you would think about as a regular cylinder. Technically, the base of a cylinder can be any curved shape, just not a polygon. It doesn't have to be a circle. It could be an ellipse or any other crazy thing you want to make up. And then it doesn't have to go straight up and down. That's the right part of it. Right means it does go straight up and down. If it's tilted off to the side, that's oblique. A lot of information there, but when you read this right circular cylinder, that's just the College Board being super precise. It really just means what you would think of when you would see the word cylinder. I have to optimize. Once again, I have too many input variables. I have an R and an H, not allowed. In the problem, though, it says the sum of the height and the circumference is 30 centimeters. So 30 is equal to H plus 2 pi R. I can then use that to eliminate one of the variables in my volume equation so that I only have one input. So I'm going to say 30 is, 30 minus 2 pi R is equal to H. I'm going to take that, plug it in up here, and then I'll have just an R. Everything will be in terms of one input variable. V is equal to pi R squared times 30 minus 2 pi R. And so now I have my equation in terms of just one input variable, so I'm really ready to take the derivative and find those critical numbers. But I'm going to clean this derivative up just because I think that'll make my life a lot easier if I do. Or I'm sorry, I'm going to clean this function up before I take the derivative. This is going to be 30 pi R squared minus 60 pi R cubed. Then I take the derivative of that. Wait a second. I'm ahead of myself here. That's not a 60. That's just a 2. Hopefully you're looking at it and thinking, what are you talking about, Mr. Shields? That's not even close. Where'd you get 60 from? Getting ahead of myself. Sorry. If I distribute here, I just get 2 pi R cubed. 30 is not being distributed. Is not being distributed, but the pi is, so this should actually be squared here with my pi. There we go. Now we take the derivative of that. It looks ugly, but remember that the pi and the pi squared are constant, so hopefully not too bad. V prime is equal to 60. There's my 60. Pi R minus 6 pi squared R squared. Set that equal to 0 and solve. I can factor some stuff out, make this a little easier. Factor out a 6 pi. Actually factor out a 6 pi R. And then that's going to be 10 minus pi R. Set each of those equal to 0. First one, of course, is just going to give me R equals 0, and the next one is going to give me that R is equal to 10 over pi. Now, certainly, I don't have a maximum volume if the radius is 0, and this is my only critical number, so I feel like I'm safe to say, okay, this is the only other critical number. I feel like that's going to be the one that's a maximum. We could always set up our intervals and test and double check that that is in fact a maximum, but I feel like we're safe to say it will be. All right, now we're talking about the mean value theorem. So before we get into the specifics of this problem, let's just say, what is the mean value theorem? Well, the mean value theorem says that there has to be a place where the instantaneous rate of change, the derivative, is equal to the average rate of change, the slope of the line connecting the endpoints. So I have change in y over change in x. Now this only works if the function is differentiable, which I have a cubic function, so that's certainly differentiable. There's no cusps or vertical tangent lines, and there's nowhere that it's discontinuous where we would have a hole, a jump, or a vertical asymptote. So what is So the question says, guarantees the existence of a C value such that f prime of C equals what? Well, they're just saying f prime of C equals this. So what's this in this case? Well, A is 1, B is 3, and if I just plug in, f of 1 is going to be negative 1, and f of 3 is going to be 19 if I did my math right. So I just plug that in, 19 minus negative 1 over 3 minus 1, and I'm going to get 10. So 10. All right. Next one. Whoa. Another mean value theorem question, although this one's bringing in the intermediate value theorem and the extreme value theorem. So which of these could be false? And so as I read through them, the first one, well, that looks exactly like the mean value theorem that we just went through in the last one. So that one seems good. So this one seems true. Next one, intermediate value theorem. Well, the intermediate value theorem is just about how, like, you have to go through all the values in between. And so usually they just give us a value, like, okay, why does the function have to have an x-intercept here? Why does the function have to equal 6 here? And so here they give me this kind of strange formula. But if you look at what that is, that's the y value of the left endpoint, that's the y value of the right endpoint, and you're adding them and dividing them by 2. So you're finding the average of the endpoints, and certainly that has to be between the two endpoints. The intermediate value theorem says you have to cross through everything between the two endpoints. And so yeah, that also seems to be true. By the extreme value theorem, there is a value c such that g of c is greater than or equal to g of x for all x on the interval. Well, that's just saying there has to be an absolute maximum, which is what the extreme value theorem says. And the extreme value theorem also says there has to be an absolute minimum. So those both also seem to be true. So at first glance, all of these seem to be true. And so what we have to think is, wait a second though. First of all, they can't all be true. Second, can I actually apply these theorems? The intermediate value theorem and the extreme value theorem require that the function is continuous. The mean value theorem requires that it's differentiable, which of course also needs it to be continuous. Differentiable. So I need to check that. And if I'm thinking about continuity, there's not going to be any holes in this function or vertical asymptotes. The only issue with continuity is, well, where does this thing actually exist? And that's all just going to be determined by, is this piece underneath the or underneath the radical positive? And so if I'm going from pi over 2 to 7 pi over 4, and I think about my cosine graph, it's looking something like this. Pi over 2 is here. And then 7 pi over 4 is somewhere right about here. And so at first I'm thinking, okay, well, part of this is negative, but I'm adding 1 to it. And the smallest value we ever have here is negative 1. And so as long as I add 1, then I'm going to be at least 0, which means that we're all good. So we are in fact continuous, so all of these should in fact be true, which leaves this to maybe not be true. So why would this not be differentiable? Why would it not be differentiable? Well, it wouldn't be differentiable if the derivative for some reason fails to exist. And if you take the derivative here, it's fairly ugly. You've got to use chain rule. You're going to get g prime 1/2 1 plus cosine of x. And if you need to write out the chain rule, please do that, to the negative 1/2 times the derivative of the inside, which is negative sine of x. And so as I think about that, that's really negative sine of x over 2 root 1 plus cosine of x. Now, we just looked at the fact that this function inside here is in fact going to cross the x-axis on that interval and thus be 0, and thus the derivative be undefined. So this one actually ends up being false because it's not differentiable on the whole interval. Very sneaky one. I love it as a review because it really forces you to think about what do each of these things mean and when are they true. All right. They give us the graph of f double prime. They ask where we're concave down. Well, f is concave down whenever f double prime is negative. So this is actually super straightforward. Always so important to read the question carefully. What graph did they give me? What graph are they asking about? I can see that this is negative between negative 2 and 1, or below the x-axis, and between 1 and 3, and that is the last option here. Nice. Where do we have a relative maximum? Well, I need to know where my critical numbers are and where we change them from positive to negative. So f prime is 3x squared minus 6x. Set it equal to 0. Factor out a 3x. We get x equals 0 and 2. And so I could set up my intervals and test to see where does the derivative change, not where's the original function, but where does the derivative change from negative to positive. I always like to think about the graph if I can, though. This is a parabola that opens up that has these two x-intercepts. I need a relative maximum, so I need to change from positive to negative on the derivative. I feel like I may have said that backwards a second ago. I need the derivative to change from positive to negative, to go from increasing to decreasing. That happens here. That's a maximum. It's not a maximum on the graph I've drawn, because I've drawn the graph of f prime. It's a maximum on the graph of f. So 0. All right.